Hello, Melita. Hello, Cheska. Hello, Avani. Hello, hello. Hello, Chris. Good afternoon, Melita. Good afternoon. How are you? Oh, I missed someone. Wait, sorry. Good afternoon, Matthew. Good afternoon, Marilyn. Good afternoon, Avani. Good afternoon, Yavi. All right. We've got Melita. We've got Cheska. We've got Avani. We've got Amanda. We've got Chris. We've got Arte. Okay. I think I can actually. Did I say good? I'm sorry. Good afternoon, Yavi. Did I say? I'm sorry. Good afternoon, Amanda. Oh, how you? Good to see you too. All right, excellent. Also, sorry, Melita. Do I say Melita or Melita? I'm sorry. Either one.
Lolita,
Okay, Melita. Okay, all right.
thank you.
So good to see. Thank you. Okay, good to see you all. I think we could just get rolling here. So here's the plan. We're going to go. As you know, there's no new homework due today. The new homework is due a week from today. We also don't have. Oh, but we have classes. Oh my God, how's that going to work? It just occurred to me. Okay, well, anyway, we don't have classes on Monday, but I know Tuesday's a Monday schedule. But that just occurred to me. I don't know. I'll have to post something about that. I don't know how that's going to. All right. Well, I'm just realizing right now as I'm saying this. Hello, hello. Someone's here. Sorry. I was just about to get to business, and we will get to business. But just as I was saying that, I'm not sure how we're going to meet on Tuesday, which is Monday. So stay tuned for that. I'll have to post something. Oh, yeah. Okay. Fair enough. And actually, Chris, I mean, it may be Chris might win that vote. I mean, of course, if there's no class, there will be a video. I hate to do that again, but because of course Tuesday is not Monday everywhere in the world. It's only Monday at John Jay. Anyway, all right. I don't want to get bogged down in that now, but that just occurred to me. So stay alert and look for Google alerts about that. Anyway, um, anyway, we're gonna get straight to business here. The business is to get back to homework 6, to continue going over, working through solutions to problems in homework 6, the big old duck constant acceleration assignment. However, I want to segue from what we were doing 2 days ago. 2 days ago, we established Galileo's principle of relativity. There it is. Okay. 2 days ago, we had kind of open conceptual day. The punchline of Monday's discussion, the punchline that informs physics for the rest of this class, for the rest of the next class, physics 204, for all of physics from the year 1626 AD all the way through 1905 into the 21st century. The foundation of classical and modern physics is this idea called Galileo's principle of relativity, which can be said many different ways, which we are going to say many different ways. But the first and fundamental form of the statement, the first form of Galileo's principle of relativity is that the laws of physics are the same in all inertial reference frames, which is to say, the laws of physics are the same in all unaccelerated perspectives or in all unaccelerated coordinate systems, which really means, in turn, the laws of physics are the same at all constant velocities. Whatever constant velocity you're going and from which you observe the world, the laws of physics don't change. If you're going 0 miles an hour compared to planet Earth, or you're going 600 miles an hour compared to planet Earth, the laws of physics are still the laws of physics. Okay, now, that is the principle of relativity. I'm going to say it again and again for like the rest of my life. Every time I say it, part of you hopefully should think, or every time I say it, part of me thinks, well, that's duh. I mean, that's totally obvious. I mean, of course, the laws of physics, whatever they are the same, right? I mean, like, who wouldn't think that? Maybe nobody wouldn't think that. But what you got to realize where this carries us into physics, it is meant to be obvious. We should think it's true. We should think it's so true that it's not even worth thinking about. Except that if it really is that self-evidently true that whatever the laws are, they are, then we got to realize that's the reason that Galileo ever had to bother to say this to anybody, is he was trying to remind people or convince people that even if the earth were moving, even if the ground below our feet were moving continuously and continually past the sun at 65,000 miles per hour, there's no reason we should feel it. There's no reason we should ever get any sensory evidence of the earth moving past the sun at 65,000 miles an hour all the time, even if it turns out that the sun is moving past the galactic center at 650,000 miles per hour all the time. There's no reason we would ever have suspected that. There's no reason we would ever feel or sense that, because the laws of physics don't change from one speed to another, right? So the principle of relativity initially comes out of trying to establish the idea that whether the earth is moving or not, our experience of it would be the same. So the first form is what I just said. The laws of physics are the same from all perspectives. The second, I'm just reviewing quickly to get to where we are today. But you really do, again, this is conceptual, but honestly, again, this is the anchor, this concept of what motion really means and how motion really works is what separates physics from math. I'm not saying physics is better or worse than math, but I'm saying math is the language of physics. Physics is about something other than just math. Physics is about motion through space and time. And the way we measure and analyze and predict motion through space and time is, first and foremost, we have an understanding of what we mean by motion. That understanding comes from this principle. The first form of it, I just said. The second form of it, another way of saying it, but a way that logically follows necessarily from the first way. The second form, and I want you to know this, like you could have, I assume that somewhere this will be in the first exam. And I'm hoping it's in your notes somewhere. And I'm hoping that if you ever ask me to, I'll write it again for you or blah, blah, blah. But the second form, the second way Galileo ever said it, the same idea is that no experiment could ever be designed nor performed in order to measure the absolute velocity of a single object, of a solitary object through space. What I mean by that is, well, and it follows directly from the first form. What I mean by that is, if the laws are truly the laws, are the laws, regardless of what they are, regardless of how much more advanced they get technologically years and years from now, et cetera, whatever the laws are, if the laws aren't going to change from one velocity to another, then if I'm on an airplane, if I wake up in the middle of the night on an airplane, or, in the thought experiment of train of thought, but like in real life, if I wake up on an airplane and it's all dark outside and blah, 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 and I know it's supposed to be a very long flight, and I wake up and I don't know if I'm still in mid-flight or whether we have already landed or whatever. And I look outside and I see clouds moving. So it's not dark, I guess. I look outside or something and whatever. And I see clouds moving outside the window of the airplane. So I see the clouds moving. There's no denying that. So I say to myself, I know something is moving somewhere in the universe. Like there is motion, no doubt about it. There is velocity, no doubt about it. But I say to myself, hang on, what's actually going on? Like, is it that I'm actually sitting still and the clouds are moving to the west? Or the clouds sitting still and I'm in an airplane that's moving to the east? If I ask myself that question, what's actually going on? What is this airplane doing? Not in comparison to the clouds, but what is it doing as a solitary object, like just through space? If I were to ask myself that question, which arguably in a way we all at some point or another ask ourselves, like in all kind of various real life scenarios, if I ask myself, what's the plane actually doing? What the second form of the principle says is, well, you might want to be a scientist about it. Galileo certainly wants us to be scientists about things. You might want to be a physicist. You might want to conduct a small experiment to figure this out because, what do you know? We should trust experiments. And Galileo is the father of classical experimentation. But Galileo says, as much as I believe in experiments, and as much as from here on in, I think that the right way to figure things out in science is experiments. Any experiment you would do right now to figure out whether the plane is actually moving through space or the clouds are actually moving through space, any experiment you do is doomed to fail, Galileo says, the second form says, because whether you consider the simplest possible experiment or the most complicated, let's consider a simple one. If I just drop an object, thinking to myself, I know I'm going to drop an object because I know what an object would do upon being dropped if I were just sitting still in a parking lot. If I dropped, hold on, I'm just going to change the movie screen. Sorry. Okay. If I were to drop an object standing in a parking lot, stationary in a parking lot, and I drop an object, I know enough about gravity to know the object is just going to fall straight down below my hand and land on the ground directly below my hand. That's what an object would do if I were standing still in a parking lot. So I might say to myself, well, let me do that. And then if the object lands on the ground below my hand, then I know I'm just standing still, because that's what an object would do if I were actually standing still. But the problem with, well, no, I'm going to pause and ask you. I just want to see if we're still all together here. What's the problem with that? Why can't that experiment work? And I'm asking you to tell me in the chat or something, or shout out or whatever. Why can't I say, since I know what an object would do if I were standing still and I dropped it, why can't I drop an object to find out whether or not I'm actually standing still? What is the problem with dropping an object? I'm in an airplane. What's the problem with conducting a simple experiment and saying, if I drop this object and it lands on the ground, that means I'm standing still, because that is what an object would do if I were standing still? What's the problem? Why can't? Well, gravity, good thing to say, very good thing to say. Gravity is the reason the experiment will work. I mean, gravity is the reason that the object will fall down. And gravity is the reason that the object would land directly below my hand if I were standing still in a parking lot. Okay, and I'm looking. So gravity is very involved in the experiment. And therefore, okay, so to take it one step further, what Avani's saying. So Avani, I think I'm with you. To put it in the simplest possible terms, then. But I mean, no, Melinda, you're right. That gravity is what we're using here. Absolutely. But I think gravity is helping us. I'm not sure gravity is a problem. But what Avani's saying, Avani, therefore, I guess what I'm asking is, to be as straightforward for everybody as possible. If the plane were actually moving, right, and I were in the plane that was actually moving, where would the object land? Would the object land directly, but how would the result of the experiment compare to if I were just standing in a parking? I'm largely asking Avani because I think she's right. I just want to sort of get to the end of the point. Like, therefore what, Avani, I guess is what I'm saying. Therefore, what would the object do? If I were in an airplane that were moving, and I'm not trying to single you out, Avani, but it's great what you're saying in the chat. Therefore, therefore the object would the object land directly below my hand, even if I were in an airplane that was going 600 miles an hour? If I were in an airplane going at a constant velocity of 600 miles per hour, and I'm not trying to trick you, and I drop the object, given what you're saying, Avani, where would the object land? Like, would it fall in a straight line and land directly below my hand? Or anybody can answer, but wait, let me see. Yes, exactly. Okay, just to make clear. So thank you, Melita, and thank you, Avani. Yes, the thing I'm just trying to drum into everybody to make sure is what form number 2 of Galileo's principle of relativity is saying now. Form number 2 is now focusing our attention on experiments. And it's saying, here's the thing. If you believe form number 1, if you believe all the laws are the same, no matter what speed you're going, then all experiments are going to follow the same laws and work out to the same results, no matter what speed you're going. So as Avani is spelling out here, that means if you try to do an experiment to figure out whether you're actually moving or not, you're doomed, because the experiment is going to turn out with the same result, no matter what speed you're going. If you're standing in a parking lot and you drop your keys, they'll land directly below your hand. If you're standing in an airplane and it's going 600 miles an hour past the earth and you drop your keys, they're going to land directly below your hand. And again, that's why we're willing to get on airplanes in the first place, because the laws of physics are the same, no matter how fast we're going. So we're not bothered by the fact that we're in an airplane. So Avani's correct, is number one. And both Melita and Avani should submit for points for their participation. There's like at least 3 portals each of them can submit to for points. So thank you both. But then what I'm saying is form number 2 then says, it doesn't matter if about technology or what experiments you have or have not thought of yet. There isn't a possible experiment that you could conceivably do to figure out who is actually moving. All you know is either you're moving past the clouds or the clouds are moving past you. There's some relative motion between the 2 clouds. That's all experiment can reveal. So then it goes to form number 3. Again, I'm just reviewing from yesterday or from Monday. Form number 3 says, well, therefore, since we are now an experimental science, since this Galileo is starting up classical physics, he's giving us the experimental technique, scientific method, all in the same lifetime as he's giving us these principles. So ever since Galileo, we take experiments so seriously. That's what distinguishes physicists from philosophers or mathematicians or theologians or political scientists or whatever. Like, we only believe what we can get out of experiments. Then Galileo says, well, if there's no experiment you could ever do to figure out how fast and in what direction one object is actually going, then that must mean, form number 3, there's no meaning to the actual velocity of a single object. That from now on, I'm just reviewing again here, I'm saying form number 3 says in English, from now on, all velocities are relations between pairs of objects. Velocity is only meaningful as a comparison between one object and another. Velocity is a relation between one object and another. Velocity is never a property of a single object. It is not meaningful anymore ever to say, how fast is the Earth going, period. No. How fast is the Earth going compared to the sun is a meaningful question. Or how fast is the Earth going compared to Jupiter is a meaningful question. Or et cetera, et cetera. Velocity is a relation, not a property. That is what it's a relation between 2 objects. It is not a property of one object. That is what we get from form number 3. Now we're going to start applying this to physics in general. Again, this doesn't sound like math, right? But please remember, again, I think what you're already starting to see in some of the early homeworks is the math isn't the hard part of physics for most people. The algebra, the crunching the numbers, we all think that's going to be the hard part of physics. That's not the hard part of physics. The hard part of physics is knowing how to set up the math, how to begin the problem. And what I'm here to tell you is how to begin problems is to use the concepts, the fundamental principles of physics, such as this one, relativity. So now we're going to start using it to see how to set up and think about the math in situations such as homework number 6. The way we're going to make that transition, the last thing I'm going to do before we get back to homework number 6 is I'm now going to give you, I hope you're following this, I'm going to give you the 4th form of Galileo's principle of relativity. Monday, I gave you the first 3. I just reviewed them. Now I'm going to give you what I call form number 4 of Galileo's principle of relativity, form number 4. Okay, again, this is all one principle. It's different ways of saying it that push us farther and farther down the physics path. This 4th form, however, is going to be the first one, is going to be the one that starts to look mathematical. It starts to show us how to use these things mathematically in problem solving. This form number 4 has 3 cases to it. So I hope you're following the organization of this. Like, stop me if you're not. We're still talking about Galileo's principle of relativity. It's not an equation. It itself is not a law. It's the law of laws. It's not a definition. It comes before definitions. It's not an equation. It's what gives us equations. But this form number 4 has 3 cases. I'm going to give them, and we're going to use them from now on. And they're mathematical looking. Here's the 3 cases. So here we go. So form. So this is Galileo's principle of relativity Form number 4, case one object. Oh, wait, sorry. Wait, sorry. I have to say one thing. Okay, so I'm at from here on in, let a, lowercase b, and lowercase c stand for 3 distinct objects, each of which has its own velocity, like its own speed and its own direction, right? Then, with that in mind, case 1 of Galileo's principle of relativity, form number 4, case 1 is the one object case. It simply says this: if you only have one object, if you have one object, call it object A, then necessarily the velocity, oh, I should pause. When I draw an arrow over a letter, I mean that it's I'm emphasizing that that letter stands for a vector quantity. I'll put that up here. Okay, for piece of notation, from now on, whenever I put an arrow over some letter, from now on, whenever I put an arrow over a letter, I'm emphasizing that that letter stands for a vector quantity. I'm emphasizing that it has magnitude and direction. So it's just emphasizing that I'm really talking about velocity here, not just speed. Okay, that's just a notation. So case 1, if you have one object, let it be known as object A. The velocity of object A relative to object A is always 0. Okay, this is so if you only have one object, if from now on we're saying, okay, actually I'm going to write that down. I'll write it down again, but I'm going to write something more. Put it in the chat. I'm sorry. Oh yeah, I'm about to explain right now. Great question, Chris. Well, the answer is it means velocity of A relative to A, but I'm introducing it right now for the first time. You didn't miss anything. Like that's literally what I'm about to explain right now. So great question. Okay. This is so important. I'm going to put on the next page. I don't want to crowd this. Chris's question is exactly the right question. And just to be clear, like I have never said it before. I'm saying it now for the first time. Okay, so I'm going to make this. So from here on in, the larger thing I'm trying to say is from here on in, we don't view velocity as something that one object has anymore. We only and always view velocity as a comparison between two objects. So from here on in, whenever we're being careful and whenever the problem has like any kind of intricacy at all, we always put two subscripts after a v, after a velocity symbol. And the two subscripts denote what two objects are being compared to each other. So to be as clear as possible, on the next page, I'm going to say, like, from now on, in this notation, I'm just defining the notation now. If we say, I'll use any two letters, whatever. If we say velocity, well, all right, if we say velocity of A relative to B, we mean okay, what I'm saying here, this is like a notation thing now. From now on, I mean, sometimes we can get away with being casual. Like sometimes things are totally obvious, but when we're being careful, from now on, velocities have they have two subscripts after the v, because from now on, velocities mean comparisons between two objects. So from now on, and the order does matter. So from now on, if I write VAB, what I mean is all these three things that I just wrote on the board here, and they all mean ultimately the same thing. I mean, if I write VAB, I mean the velocity of object A relative to object B, or put another way, the velocity of A compared to B. What does that mean? That means the velocity that would be measured for object A by object B. It means the velocity that we would measure for object A if we were measuring from the reference frame, i.e. the perspective, i.e. the coordinate system of object B. It's what object, if I say VAB, I mean what object B would observe and measure as the velocity of object A. If I say VAB, I mean the velocity of A from B's perspective. And finally, another way to put that is, I mean the velocity of A if we assume that B is sitting still watching the world go by B, right? So again, those of you like play a lot of video games, or watch a lot of movies. Movies take advantage of this idea, or deploy this idea all the time, and certainly video games do. Right? Often, and the way video games use the terms first person and third person still actually confuses me to this day. But so I'm not sure that they're using the terms exactly the same way I would in my, but like you can do a video game from what they call, or many of you can do a video game from like first person perspective, meaning that you like are just there and the world is going by you, right? Like you don't watch yourself walk around it in Minecraft or I mean, it's like a ridiculous example, but and certainly Fortnite, I think. But like, you know, Minecraft, you can toggle it so that you don't see your figure walking around the screen because just like in the real world, you don't see yourself walking around the world. Your nose is always right in front of your eyes, right? Your arms are always in front of your face or like near your face. You, as you go forward, you just see the world go back past you, right? And that's because you're looking at the world from your perspective. That's what we're talking about here. The thing we're saying in physics, what we're starting to say in physics is it totally matters what perspective you're in when you measure velocities. The thing that we're really adding in physics that's sort of the mind blower is we're saying that all these different perspectives from which you can view the world, that they're all equally correct. That it's not like some of them are tricks and some of them are illusions and others of them are like real. We're saying, oh no, they're all equally real. So anyway, if I write velocity, and in fact, we're saying there's no other way to talk about velocity other than from a certain perspective. That if you're, I hate to use video games examples all the time. I apologize. I know not everybody plays them, and I never did play them but I have 2 children, and they're a big part of our lives now. So I mean, the video games are so it's a frame of reference for me. That when you switch back and forth between first person perspective or third person perspective, say in Minecraft, if that means like you have what I'm trying to say right now in physics. Okay, cool. All right, good. Thank you. Okay, fine. So like part of what I'm trying to say right now is that ability that we have in video games to look at things from the perspective, like from our own perspective and watch the world go past us. What I'm trying to say is that is not any less correct or more correct than fixing a camera to planet Earth and watching you go by the camera. It's not like one of those is correct and one of those is incorrect, like really on a deep scientific level. Because even if we think, well, come on, obviously I'm going past the tree. The tree is not going. Sorry. If you think to yourself when you walk past a tree and you see the tree move past your eyesight, you might in your brain think, well, but I know the real truth. The real truth is that the tree is standing still while I go past it, even though it looked like the tree is going past me. What we're here to say is no, because the tree is fixed to planet Earth. And didn't you decide in 3rd grade to believe that the Earth itself is not actually still, right? And it isn't. The Earth is not actually the correct frame of reference any more than you are or the tree is, right? Everything is a matter of perspective. You cannot get outside. You can't jump outside the tree or jump outside Earth or jump outside first or third perspective and then like actually do 4th person perspective and actually see everything the way space does. Literally what we're saying now in physics is that's meaningless. That is not a perspective. Everything is a perspective. Therefore, to bring it back to bring it back, when I write from now on VAB, what I mean is the velocity of object A as it is observed by object B. And what that really means is the velocity that we would observe or measure for A if we treat B as the stationary perspective. That's what frame of reference now really means. It's the perspective or coordinate system maintained by an observer who is designated, assumed, hypothesized to be still. Yeah, and I keep saying that, like a perspective is from a frame of reference is a coordinate system maintained by someone assumed to be stationary. And then you might say, well, what do you mean assumed? I mean, are they actually stationary or not? And I'm here to say, it depends what you're comparing them to. All we can ever do is make a choice. I'm getting tongue-tied on this. But so from now on, VAB means velocity of A relative to B. It means B is assuming itself to be at rest and it's looking, so it's first person perspective from B. And B has got a camera fixed on A, B is watching A, and B is reporting the velocity of A. That's what velocity of AB in general from now on means. Therefore, to go, sorry, there's something in the chat. I think that was what, yeah, okay, thank you, man. I'm so psyched that man said that. Okay, so that's notation. therefore, I'm saying, to go back to case one, again, I'll write it again. So therefore, case one of GPR Form 4, case one, the case when you only have one object. If you only have one object in the world, call it object A. According to case one, then, the velocity of object A relative to object A, right? The velocity of A relative to itself, if you're following, well, hello, getting excited there. If you're following the logic of this, and if you do play video games, you know, if you're in first person perspective, the velocity of you compared to you is always necessarily, by definition, zero, right? Like, if you're getting what I'm saying, you almost would think that is obvious, maybe, right? The viewer is by definition not moving. So if we own, so this is just another way of saying all velocities are now comparisons. If you only have one object, you don't have anything to compare it to. You can only compare it to itself. Then what it's doing is it's not moving. What is planet Earth doing? Really? Relative to itself? Nothing. Compared to itself, it's always there. Right? You get my point. I think you get. So that's the one object case. It's just a mathematical way of formalizing what we're trying to say about relativity. From now on, relativity doesn't apply to single objects. So let's go to case two. Case two would be the two object case, right? Like, basically we're saying we need at least two objects to talk about velocity at all. So this would be the two object case. So now we have a case where we have two objects, A and B. So what I say here is velocity of A relative to B. What can I say about that? Here's what I'll say about that. What it always and necessarily is equal to is the negative of the velocity of B relative to A. Okay, this is a truism from now on. This is a principle. Again, if part of your brain is thinking like, oh, well, duh, well, then good, you're with me. None of these is meant to be a new idea. All, especially if you play video games or watch movies or like live on planet Earth. Everything I'm saying, if we're doing physics right, every time I say anything, part of you should be thinking like, yeah, I kind of already knew that. I kind of even thought about that once when I was in kid. I didn't know I was thinking science when I thought it. I didn't actually think it was like a big deal. But well, I'm here to tell you it is. And this is what physics is about. Physics is about noticing the things that we all agree on, but then realizing which ones of them actually are big deals and lead to a lot of surprises. Okay? So every step along the way should. So I'm saying now, what I'm saying is what I think you know. If you observe me go past you at 100 miles an hour to the east, then necessarily I observe you go 100 miles an hour to the west, right? If you see me do that, I see you do that, right? Necessarily, the velocity of me relative to you is just the opposite. It's the equal magnitude, but opposite direction of whatever you see me do. And I'm saying both of us are correct. The Earth can say that, the sun can say that the Earth is going past it at 65,000 miles an hour to the west, to the east, and the Earth can say that the sun is going past it at 65,000 miles an hour to the west. And from each of their perspectives, they're each correct. All right, so that's the two object case. You kind of already, now the three object case is where it gets interesting. And I'm going to write it down. I'm going to try to give a quick example of it, and then you're going to see it for the rest of your life. We're going to start using all this as I return to homework 6. But the three object case is a little less obvious. So that was case 1. So the three object case, case 3. So now we have three objects, A, B, and C. How does this work? This says this. If you have three objects, the velocity of A relative to C, okay? And A, B, and C could be any three objects, any three at all, with just three distinct velocities. So the velocity of A relative to C necessarily equals the velocity of A, B, or the velocity of A relative to B, plus the velocity of B relative to C. Now, this we need to talk about for a second. Again, it's going to come up a lot. It comes up a lot in physics 204. The way I'm writing it, why is the screen just freeze? Wait, oh, I see. Okay. The way I'm writing it, as usual, it almost looks like self-evident. It almost looks like the property of transitivity or something like that. It looks like a pattern, like AB plus BC equals AC. But like, what am I saying in English? What I'm saying is, well, I'll put it in velocities add together in the manner of vectors but the reference frames okay. In English or in summary, what I'm saying is, it turns out, since all velocities are relations between pairs of objects, velocities can add together. They can add together and follow the laws of vector addition. Velocity vectors can add in the way that any vector quantities can add, and we're going to do more and more of that later on. So velocities can be added, but they can only be added if their relative character is respected. They can only be added if the reference frames from which we're adding them are organized in a particular way. So what I mean is this. I'm saying velocities can add, or you can add together velocity. By the way, everything I'm writing right now, again, I'm going to apply it back to homework 6 and future homework. But from now on, this is all a principle. So anything I'm writing right now, part of its purpose is that this all counts, or should count, or will count as step 3 GDP whenever you're solving a problem from here on in. Often, if you're not quite sure how to begin a problem, especially like of the kind that are in homework 6 or definitely in homework 7, if you're like trying to set up a problem and you don't really know how to set up the math or what equations to use, they look simple maybe, but these are often the starting steps. Like after you've written down after you've written down the diagram and fact pattern and written down what the question is, if you're looking for what's my step 3 GDP, you have a list of equations already, which I'll review soon. You have like V bar equals V naught plus V over 2, blah, blah, blah. But now add these to that list as well. These 3 statements, even if they look obvious, I hope whatever they look like, they count as step 3, very important step 3 GDP choices. Anyhow, this one, possibly the most complicated, possibly the most powerful of them. This one says that you can add velocities together. But when you do, you have to be really careful about which velocities you add together, and you have to be careful about what the answer means. So, for example, I could throw a tennis ball like past the screen right now, or whatever. I could throw a stylus past the screen right now, and I could throw a phone past the screen right now. The stylus might have a velocity of 30 miles per hour. The phone might have a velocity of 40 miles per hour. Okay, can I add those two numbers? Well, I could add those two numbers. I could add the number 40 and 30, I can get 70. But it won't mean anything in physics to do that. I can't do that because I have to be careful now. If I throw a stylus past the screen, the stylus from here on in, we would say, is going 30 miles an hour relative to the screen. Like the stylus might be object A, and the screen might be, let's say, object C. And we would say that the stylus, the velocity of the stylus relative to the screen, VAC, might equal 30 miles per hour, okay? But then if I throw the phone, and I say the phone has a velocity of 40 miles per hour, well, the phone is object B. It's also moving if I say it's got a speed of 40 miles per hour, I also mean relative to the screen. Or if you don't like the screen, I mean relative to the laboratory that I'm sitting in right now, or relative to planet Earth, whatever you want, or relative to my bedroom, whatever you want to say. The point is that if I throw this stylus and I throw this phone, both of their velocities are being measured in the same frame of reference. Whatever you see and maybe that frame of reference is you, let's say. You observe the pen go 30 miles an hour. You observe the phone go 40 miles an hour. So you can add the numbers together, but you wouldn't, and you could get the number 70, but it wouldn't tell you anything about the physical world. There's nothing in the world that's going 70 miles an hour just because this pen's going 30 and this phone's going 40. My point is, if two objects are going in the same, or if two objects' velocities are being measured in the same frame of reference, it doesn't mean anything to add them together. But if you have two different frames of references, so you can't add VAC to VBC and expect to get anything. What you can add is a VAB to a VBC. Then you can expect to get something. What do I mean? I mean, like, you could be going 20 miles an hour relative to a subway train, right? Like you could be on a subway train, like what, or 2 miles, right? Well, let me give you, I'm sorry, even a simpler case. You could be going 0 miles an hour relative to a subway train, i.e. you could be sitting in the subway. You're going 0 miles an hour relative to the subway. But the subway might be going 80 miles an hour relative to Manhattan, right? So it's like you're A, the subway is B, Manhattan is C. You are going 0 relative, A is going 0 relative to B, B is going 100 relative to C, and therefore, guess what? You, object A, are necessarily going 100 relative to C. That's why you take subways, because you can do nothing and still get there, right? I mean, it's like totally obvious, of course, but it's not obvious that it's important. What I'm saying is you take subways because you believe that velocities add. You believe the velocity of I shouldn't say you, I don't know what you do. I take subways because I believe that the velocity of the subway will add to the velocity of me without me moving a muscle at all. And therefore it'll get me home because the subway and I are two different frames of reference. I believe, right? And I believe that in the simple case of 0. 0 plus 100 equals 100. Velocity of A relative to B plus velocity of B relative to C equals velocity of A relative to C, right? Now, that's obvious in a way. Like, why do we have to? But what I'm saying, what's not obvious is that this equation that just captured that simple case, like I just gave the simple case of one object being stationary relative to another. I give a simple case where one of the numbers was 0. But the thing is that this equation works, or this principle works, even if none of the numbers is 0, even if some of the numbers are negative, or even better, even if the different velocity vectors are actually pointing in different dimensions along different axes of space, this all ends up working. That's what you probably are already starting to see in the lab, but you'll definitely see in the next lab and here. Like, it's like, even that if you get up on the subway and start, or on an airplane, if the airplane is going 500 miles an hour past the ocean and you start walking backwards on the airplane, so you're walking 2 miles an hour negative on the airplane, you're now only passing, well, maybe you don't know because it's an airplane. I'll go back to this. On the Columbus Circle escalators down to the subway, that the reason sometimes you get in the left lane of the escalator while all these tourists are just chilling in the right lane of the escalator, you get in the left lane and you start running down the escalator because there you're assuming the velocity of the escalator will add to the velocity of you even when you have non-zero velocity, right? If you're going 2 miles an hour down the subway relative to, if you're going 2 miles an hour down the escalator relative to the escalator, while the escalator goes 10 miles an hour relative to Columbus Circle Mall, then you're going 12 miles an hour relative to the Columbus Circle Mall. That's why you get to the bottom, faster than the person standing in the right next to you, right? And you also know, if you were ever a little kid or one of my sons, if you run up the down escalator, don't do it when it's crowded. You know that if you run up the down escalator and you do it exactly right, and you make it into a fun exercise, if you time it exactly right, you can look like the road runner, like moving your legs while someone, or at least my kids used to do this to me. Like someone watching you from above will see the escalator going down at 5 miles an hour positive, while you're going relative to the streets, while you're going up 5 miles an hour negative relative to the stairs. So therefore, someone in the streets watching you sees your leg move and sees you going nowhere. You know what I'm saying? I know you know what I'm saying. So I'm saying velocities add, but only if the frames of reference are arranged this way. The bottom line, and now I'm moving on. I know we only have 24 minutes. I'm moving on to homework 6. This is okay. But the conclusion of this, we're going to blow this up and use this in 3 dimensions soon. Right now, but to understand it and believe it and see what I'm talking about, picture it in 1 dimension. I am saying the velocity of me relative to you plus the velocity of you relative to them equals the velocity of me relative to them. That's how velocities add. Once you have 3 objects, you have 3 different frames of reference. If you organize the frames of reference in this specific pattern, velocities will add. And we all know that, we rely on it every day, but what we might not have known is it's actually a physics principle. Okay. Having said that, I'm going to spend the remaining 20. Oh, sorry. Okay. I was hoping someone would say something. Okay. I'm going to look at what Chris is saying. Yeah. Velocities separate like vectors. That's good. Definitely. They separate like vectors. They, in fact, even add like vectors. It turns out they, so yes, my fast answer to what Chris is saying is yes. Basically, velocities separate like vectors. I guess I would add to that they also add like vectors, which you'll see leads to some details. But the only other you he's kind of a comic genius, I'll say that. No, that was very smart. And honestly, I'll say this too. I mean, I'm glad. I'm glad Chris is doing that, and I'm glad anytime anybody sort of. Oh, that's what I should open up a portal for that. I'll try to remember to open up a portal for like anytime anybody tries to like stop and kind of summarize everything I'm saying. I think that's really good for everybody. I think it is kind of genius to do that. And the summary I agree with. I'll just add one thing to the summary. I'm saying velocities separate like vectors, velocities add like vectors. But the key thing is that only if we respect the varying frames of reference do they do that. Like velocities don't do that if they're all measured in 1 frame of reference. Velocities don't do that if we only have like 1 or 2 objects. Like they do that once we have enough objects, 3, to have different frames of reference. So like this whole thing that Chris is saying, which is genius, well, maybe not genius, but it's very good. And it certainly is a genius instinct that he would have the instinct to do that. And to make it funny makes it, anyway, whatever. What I'm really emphasizing in his emphasis is that velocities separate like vectors, velocities add like vectors, velocities even sort of add and behave like the way you think they do, but only once you take into account their relative quality. All of this is about trying to emphasize velocity can't do any of this stuff. Velocity doesn't mean anything or fuel any of these equations properly if it's treated as a property of 1 single object. It only works when it's when velocity is a comparison between 2 objects, when we realize that any velocity you ever write down ever or measure is from the perspective of some specific designated object. But okay. So that said, so that's more equations you can take away. That's GPR form number 4, 3 cases written as mathematical equations. Now, I mean, and definitely, I'm glad you did. If anybody else wants to stop and either summarize or say anything, that'd be great. I'm about to transition to back to homework 6. Of course, we're not going to finish it today, but we're just going to keep churning through it. So I'm going to do a different screen. Well, no, I'm not. Okay, so back to homework 6. Homework 6 is all about constant acceleration. It's called the big old duck. And that's of course, the big old duck is sort of the biggest, hardest problem on the sheet. And we're not going to get to that today, but I promise all of you, the big old duck, I think, is the hardest problem on the sheet. It's probably the most important summative problem on the whole sheet. It usually appears on exams. I promise you, we are going to talk fully through the big old duck. Just, we're not up to it yet, but we will get there. Don't worry. But what we're going to get up to now, let me just do is problem number 3. A lot of you had questions and issues about problem number 3, which is called a few bolts. You know what I'll do? Maybe this is a good idea. Okay, so I'm very quickly, just for a moment, for the sake of history or posterity or you, I'm going to quickly switch the screen share just so you can see the problem I'm talking about, just in case you lost it or someone's lost it or whatever. And then you can, I'm just going to switch for like 1 second. So if nothing else, you could do a screenshot of it. I think that would be a good idea. I should do that more. So just for 1 second, the problem I'm talking about, just so you know, is this right here on the screen. Yes, this is the problem. Yes, a few bolts. This is what I'm going to talk about right now. I'm just doing this long enough. If anybody wants to take a screenshot, or if you're watching the video or whatever, this is the problem I'm talking about. Okay, so now I'm going to go back. Oop. Okay. But I have to look at it. All right. Okay. Okay. So first of all, one thing is given in this problem, and from now on, it sort of will be given in our lives. It's the first thing that's given here, something we haven't talked about in this class yet, but it's something that you evidently, in principle, discovered in lab number 2, which was a while ago. What we found out is that when things fall, when things free fall, apparently they do change their position in time when they fall. You can see that with your eyes. Therefore, they have a velocity when they fall. Apparently, they change their velocity when they fall. You can also see that with your eyes, because at first an object is at rest when you let it go, and then sooner or later it's actually moving. So you can see with your eyes that not only does an object change its position, but it also, and therefore has a velocity, but it also changes its velocity, and therefore it has an acceleration. But what you can't see with your eyes, but yet you can demonstrate in one of various ways, and you guys did demonstrate to yourself with a bunch of bolts on strings, what you can eventually come to realize is that while they change their position and while free falling objects change their position and therefore have a velocity, and change their velocity and therefore have an acceleration, evidently the buck stops there. Evidently, they don't change their acceleration. Evidently, the rate at which they change their velocity stays constant. Now, that is not obvious at all. It's hugely, hugely important and hugely true, but it is not obvious. That's why you have to do a whole, and I might add, probably very confusing lab number 2 in order to eventually discover that fact. It is not self-evident that things, when they accelerate downward, that they don't accelerate their acceleration. I want to say that one last time. Well, I'm going to write it down. What I'm saying is, okay, hold on. I'm saying from now on, definition of free fall, when we ever from now on say free fall, as in toward the surface of the earth, what we mean is an object exempt from all no, okay, once again, I'm going to write this on the next page because I don't want to squeeze this. I'm sorry. the definition of free fall from now on. A free falling object is an object exempt from all external influences, i.e., all external pushes and pulls, i.e., all contact with any other object other than gravity. Okay, I just want to dwell on that point for a second. From now on, if I say an object is free falling, I mean it's influenced by nothing but gravity. What is gravity? I don't even know at this point. I just know gravity is the phenomenon, is the tendency that we've observed in our life that for some reason, the center of the earth seems to pull things toward it all times in all ways. Gravity is just I don't know the math of it. I don't know the details of it yet. And neither did Galileo at the time that he's developing all this. We just know that gravity is an observable phenomenon by virtue of which things, all objects seem to be somehow attracted to the center of the earth. So they always seem to be pulled down to this. So what free fall means from now on is when you release an object from any kind of touches, any kind of pushes, any kind of pulls, any kind of hands, any kind of ropes, any kind of levers, any kind of friction, any kind of surface, any kind of air friction, any kind of gas. If you let an object just be released from every possible influence that you can, or the best version you can do of that, other than the natural pull of Earth's center, which we call gravity, then that's what we mean by free fall. Okay, from now on, that's what free fall means, is just gravity. And what apparently is given from now on to us from what's apparently discovered according to Lab 2, according to Lab 2, according to Lab 2, and according to Galileo's findings, which are similar, all free-falling objects accelerate at an approximately constant rate. This is a big deal. Again, now I'm saying something that I think this is not obvious. This is not like, duh, we all agree. No, this is something that has to be shown. By this, I mean, from now on, I mean that when an object is in free fall from now on, in free fall, this is all, this isn't exactly true, but it's largely enough true. A equals A naught, right? A doesn't change when objects are free falling. So free fall is our most natural example of a situation where all these equations that we're now developing, these equations that assume a constant acceleration, like the last two equations we developed 2 classes ago, like V bar equals V naught plus V over 2, and x equals 1/2 at squared plus V naught t, like those equations that assume a value of A that is steady. Well, from here on in, the natural scenario that we can believe this assumption is the scenario of free fall. In free fall, A is a constant, and we call it from now on lowercase g. We call that constant acceleration from now on lowercase g, as in gravity, lowercase g. And it turns out that number is measurable. It's approximately 9.81 meters per second squared pointing down, right? All this, again, it's not obvious. Honestly, it's really kind of the first thing I'm ever telling you in physics. Of all the things we've said so far, we said definitions, and then we've done logic on the definitions, and we've basically tried to convince ourselves that everything we've said about the universe so far literally just makes sense if you think about it hard enough. This one, you can't just figure out by thinking. This one, this idea that the constant acceleration due to free fall, that the acceleration in free fall is a roughly constant number, and that number is roughly 9.81 meters per second squared, or 32 feet per second squared, or whatever, 22 miles per hour per second, always pointing down. That number had to be figured out in the lab, but in principle, we did in lab 2. So from here on in, we have it. Okay, and to get back to homework 6, I know we have 9 minutes to get back to homework 6, because that number is already approximate. Like, it's at the actual number, like the digits are going on forever without repeat, just like pi. And the actual number varies slightly depending on how high you are and blah, 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 blah. So since we're already rounding that number, generally speaking, in physics problems that are on paper, we generally round the number a little bit more and make it even more easy on ourselves. So if we're going back to homework 2, back to the problem, homework 6 problem, I forget which problem it was, problem 3. The assumption here is that A is a constant, which we're calling the free fall due to gravity, and we're saying here it's approximately 10 meters per second down, right? We're rounding 9.8 to 10. Physicists do that all the time. They're not lying. They're just rounding. We have to round to some digit no matter what, so we're choosing to round to that digit. Okay, so anyway, that's a given, but I'm saying it's a given in this problem now. It is one of the facts, and it really is kind of a fact from here on in, as long as we're doing physics on the surface of the Earth. So that's a given. Then what else is given? We see a bolt known as bolt A. So here's bolt A, and it's dropped from rest. So its initial velocity is 0 meters per second. It's dropped at rest. Okay, actually, I'm drawing this. I need to. Well, yeah. Okay, it's dropped from rest. At a position that I'll call x naught. I'll call 0. I'll call it y. Actually, well, yeah. I'll call it y because we're going down. And I'm going to draw one other thing. We know that bolt A is dropped from rest, and we know we're going to have this second bolt named bolt B also dropped. I know I'm reading the problem, so I know both of them are dropped. So both of them go down, and nothing ever goes up. So something I'm going to add to my diagram right now before I go any further is I'm going to add a coordinate system. I'm going to pick my frame of reference, my coordinate system, my perspective, and say in this coordinate system, I'm going to call down positive because I can, because I don't have to. I could call down negative, but since everything is happening down in this problem, I want as few negative signs as possible. So I'm going to choose to call down positive, and I'm making that clear in my diagram. So I've got a diagram so far. The other thing that goes in my diagram is that then, like sometime later, at t equals 5 seconds. Now this is a little bit hard to draw. I guess I should have. All right. I don't want to make it look like there are different heights, so I'm just going to move this over. Obviously, there's different ways to draw this. So we got this bolt A, but then we've got this one here, bolt B, and it's dropped at t equals 5 seconds, and it's thrust, so its initial velocity. is 40. Okay, and notice it's 40. It's not negative 40 because I'm calling anything that goes down, I'm calling it positive. All right, so those are the givens, right? Those are the givens, and y also equals 0 meters. Okay, those are all the givens. So that's my step one DFP. Okay. Okay, step two. What is the question? What is the question? The question is A. The question is A. How large or small is the gap? I'm sorry. And I guess we did do, I'm sorry, I forgot we did do this last time. I'm doing all this and we did it last time, but I apologize. We did this last time. I just realized. Okay, but I'm still going to use all the diagrams. Okay, we did this. I'm going to skip. Right, we did A, B, and C last time. I'm going to skip. Darn it. All right. I'll skip to D. I think I said something fast about D, but so D is sketch one neat, clear V versus T graph. Okay, which represents the motion of both bolts from the beginning of your observation from T equals 0 to T equals 7. All right, so this, what they're really asking for here, let's get this straight. Now that we're talking about relativity and everything, and I know we only have 3 minutes more, but this question D, sketch of V versus T graph, they're asking, in effect, from the reference frame, from the perspective of Earth. They want one graph that someone who's standing on Earth would make, incorporating both the bolts, each of the bolts, from the perspective of Earth, right? From the same perspective. So we're not adding together the velocity of the bolts. We're just looking at them individually, right? In one frame of reference. So here's the graph. Maybe I did this last time, maybe I didn't, I don't know. But here's the graph. If I make it my way, where down is positive, then here's time in seconds. Here's velocity in meters per second. And we're going out to 7 seconds, 4, 5, 6, 7. And the velocities are going to be like 10, 20, 30. Right? The velocities evidently increase at a rate of 10 meters per second every second, right? The acceleration. Well, okay, I'll just do the answer. And then so bolt A, it started with a velocity of 0 at time equals 0. Every second, it gained 10 meters per second of velocity. How do I know? Because that's its acceleration. It gains 10 meters per second every second. So velocity A, bolt A would do something like this, right? It would be a line of y-intercept 0 and slope 10. The other bolt, and I know we're going to wrap up. We'll keep doing this next week somehow. The other bolt does the exact same thing. It's got to have a line with the exact same slope because the other bolt has the exact same acceleration. The only difference is that it starts. I'm sorry, that goes all the way for 7 seconds. The other one starts 5 seconds later, but it starts at a velocity of 40. So it's a parallel line. It's a parallel line with a different y-intercept, right? In effect, it goes, well, it's like that. They both have the same slope. But the second line starts with a higher initial velocity. That's it. Sorry, that's as much as I can do right now because I do realize it's 4:20. So we'll just keep going with this next week. sort of ending on a dud here, but that's where we're at. So I'll hang out for a second if there's any questions. I will post something about what we're going to do about Tuesday, because it is true that I do something else at another institution at this time on Tuesday. So I mean, Chris is probably right that we're going to do something video funky instead. And but I guess so just stay tuned and I'll post it. Okay. Have a good day. I'm here for questions. If you want them, I'm stopping the recording. Yes. Yeah. All right. Well, another one. It's been a lot lately. Bye. Yes. Thank you. Have a nice day.
Oh, Professor, I have a question.
Yes. I'm going to turn off the recording.